This lab examines bar magnets and the magnetic fields they create. The goals of this lab are to gain an understanding of how magnetic dipoles change as a result of varying distances, examine methods for calculating magnetic fields, gain a visual understanding of how magnetic fields work, and use code to model interactions of bar magnets and their surroundings. A magnetic field is the area surrounding a magnet or a moving electric charge in which a magnetic force could be felt. A magnetic dipole can be created with magnets or by using loops of wire carrying current. For the latter method, the magnetic field can be found at locations on axis using this equation. Here, the pi r squared and the conventional current can be thought of as equaling a magnetic dipole constant mu. This mu is determined by the conventional current in the area created by the wire. Magnets also create magnetic dipoles in a similar way and also have magnetic dipole constants, except their constants cannot be calculated from an area in a conventional current, obviously, and instead is a material property that is dependent upon atomic interactions inside the magnet. For this reason, the magnetic dipole moment has to be determined experimentally, as done in this lab. First, a magnetometer app has to be downloaded, and the experiment needs to be set up to account for the magnetic field of the Earth. If the magnetic field is not taken into account, then the recorded magnetic fields would be the sum of both that from the Earth and from the magnet. Since the magnetic field from the Earth depends upon the exact location and orientation in which the experiment is taking place, if the phone is not aligned north to south to zero out the x component of Earth's magnetic field, then the resulting values will be significantly altered, giving incorrect constants for mu. So once true north has been determined, it is important to find the magnetometer sensor in one's phone. This is done by moving a magnet along the side until the largest values in the x and y are found. This then pinpoints the location of the sensor within the phone. It is important to determine this, as the distance from it will be important in all calculations. To begin this lab, it is necessary to collect data to use in order to better understand the magnet. First, a distance is recorded in which the magnetic field is equal to 1,000 microteslas. This is repeated 3 times, and the average of the distances is determined. From this average, distances for 1.5, 1.75, and 2 times the recorded 1,000 distance are calculated. The magnet is then placed at these distances, and the resulting magnetic fields are recorded. Once this has been repeated multiple times, the average magnetic field values are recorded as well. It is known that the magnetic field can be calculated using this formula, which emphasizes how the magnetic field is dependent on distance to a factor of n. In order to determine to which degree distance plays a role in determining this magnetic field at a location, an alternative form of the equation is used, in which the natural log of the magnetic field is equal to the natural log of the constant k plus n times the natural log of the distance r. This equation can then be used to graph our results with ln b equal to y and ln r equal to x. N and ln k are constants and can therefore be determined by looking at the equation for the line created when the results are plotted. When ln b is plotted against ln r for the average magnetic field values and their corresponding distances, the equation y equals negative 2.8x plus 0.8161 was found. From this, we can see that n is equal to approximately negative 2.8 and ln k is equal to 0.8161. By looking at the Biot-Savart law version of the magnetic dipole equation, it can be seen that n should be equal to negative 3 and k is actually equal to mu naught times 2 mu over 4 pi for an observation location on axis of the magnet. From this information, the mu value for the magnet can also be determined. This gives a mu value of 11.3 ampere meters squared. This can further be confirmed using computer-aided modeling of the system being examined. In this program, a magnet is created and several observation locations are examined around it. This is done by first establishing constants such as mu naught over 4 pi, as well as the mu value that was calculated previously. From here, a function is created that determines the magnetic field at a location using this equation. This function is then called after observation locations are created at varying locations a set distance away from the magnet. The resulting magnetic field vectors are then displayed using arrows, and the magnitude is printed for certain observation locations. The results of this code and the inputted value of mu gave magnetic fields with similar magnitudes to those seen during the data collection portion of this lab. This further proves the accuracy of the determined mu value. An extra observation location is created with an angle of 45 degrees to the magnet. The magnetic field is calculated at this location, and a resulting value of 795 microteslas was found. To confirm this accuracy, it is compared with a real-life version by placing the magnet the same distance away at a 45-degree angle from the perpendicular. This gave a value of 770 microteslas, which is only about 25 microteslas off. It is also possible to imagine what would happen if a second magnet was lined up end-to-end with the current magnet.
The directions of the magnetic field would behave in the same way, except the magnitude would now increase in all directions.